Hello everybody. The title of my today's talk is What Lies Beneath the Beautiful Code, and I'm sure it grabs your enough attention. Though the title resembles with the famous English horror movie, I guarantee that I'm not going to talk about any horror or intimidating stories. So guys, just relax and enjoy the talk, and I'm sure you will. So let's quickly introduce myself. I am Niranjan. I am a Mumbai-based Ruby ROR developer working for TCS, Tata Consultancy Services. And apart from developing enterprise web applications, I also enjoy reading, writing, music, and trekking. So that's about me. Let's get on to the talk. In this beautiful world, we often come across many things that give pleasure to our eyes. But most of the times, what lies beneath them is not, or it's hidden from our direct view. Taking an example of this tree, where we have a very entangled, complex roots underground. The language like Ruby, or I can say Python, Perl, they are no exception to this nature principle. So what is Ruby? We know Ruby is a beautiful language, it's smart. It is pure object oriented, so everything in Ruby is object oriented, and it is interpreted. Now most of us would know that the Maths Ruby interpreter is completely written in the language C, the same language that we used to study in our good old college days. I still remember struggling with pointers, structs, unions. Okay, this is called as Maths Ruby interpreter, but now we also have Koichi's Ruby interpreter introduced from Ruby 1.9. So this was mainly to speed up the performance, and Koichi Sarade actually introduced the YAW, that is yet another Ruby virtual machine. Okay, good to know about this. Maths and the team, they have put tremendous efforts in writing the C implementation behind Ruby. So all the mapping of the objects. My talk is an effort to try to understand some part of this implementation. Now a question may come to your beautiful minds that why should we know? Why should we know about this underlying implementation? Why should we care about the mappings? The reasons that I could think of is if we know the underlying implementation, the mapping between the Ruby objects and the C world, it would be helpful to understand the C extension libraries that we use in our day-to-day world in a better way, and it would even help us to write some C extensions if needed. And again, the most important point is that it is going to help me to become a more knowledgeable Ruby programmer. So that is the main point. Okay, so let's dive into the C world to explore the C things. Okay, now the first question that can come to our mind is why C? Why did Matt choose C for the implementation of Ruby? Maybe the obvious reason that I could think of is again the performance. When it comes to performance or speed of execution, nothing beats C. C often deals with lower level system details like memory allocation, deallocation, then we have the pointers thing, we have the storage areas, we have the variable types, and again C has a wonderful ability to actually manipulate the data with directly memory addresses by the use of its pointers. I should actually contact Maths to find out if there were any other specific reasons behind this. Maybe the Perl was implemented in C and that's why he could have chosen the C implementation. Okay, let's go ahead. So this is the general process, TPI, tokenize, parse, interpret. So what happens to your code when you execute a Ruby program? So you input a Ruby source code, we have a lexical analyzer function called yylex. It gives the series of tokens to the parsing engine, that is YACC, yet another compiler, and it generates an abstract syntax tree. It's similar to the DOM to a web page, and interpreter directly executes the code. Now this was the picture of 1.8, but with 1.9 the things are much improved. So we have this additional stage called compiler, So what it does, it actually compiles the AST to a byte code, and that an interpreter actually executes the byte code. We have again one difference of Bison. So Bison is also written on top of YSCC, but with some additional functionalities. So this is about 1.9. Let's take an example. So I'm using a REPL library which is readily available in Ruby 1.9 to see the lexical output and even the S expression, that is the AST, and the Ruby VM instruction sequence class to basically understand the disassembled bytecode. So this is a very simple example, just creating a string Niranjan and just assigning to another variable. So how does it look? So we have this tokenized output, we have this bytecode output, we have this parsed output, and we have this bytecode output. If you look at this, the tokenized output, that is this one. You can notice this is some array 1, 0, then we have on identifier, some string. So this is actually nothing but it's the line number, that is row, column, and we have the identifier, that is the operation, and then we have the actual string token. So at the end, what you see is all the tokens, the tokenized parser, and these tokens are passed to the Bison. This is an open source engine which passes the code to AST, and this is the output of the past one. So you can compare this to this assign, how it is converted to assign. Then we have a call to the method called dup, okay, and the end is this one is the actual bytecode. So these instructions are directly executed by the interpreter. Okay, so you can notice this is a set local, trace, get local. It's similar to the assembly language code. Take another example of creating a class. So I'm creating a class object person. So person is a constant, and I'm defining a method called name and just returning Niranjan. So how does it look? Same way, now you will notice that the keyword is class. Again, we have set a constant called person. We have keyword again def, and we have the identifier as name. The corresponding abstract syntax tree, again, earlier we were having some program, but now we have a class. Then the same thing basically. We have created a string literal, and at the end, the bytecode that it uses is actually use some bytecode instruction like define class, put special object, put object, and basically the put string Niranjan. So this is how it looks. We will take a quick glance at what the seasource available beneath the Ruby. So this is taken from readme.txt. So this is a file you can find in the Ruby 1.9.3. It basically explains what all the seasource code is available. So there are some Ruby language core codes with object.c, class.c. We have the Ruby syntax parser, parser.y, and keywords lex.c. Then we have this Ruby evaluator where we actually deal with the implementation of the virtual machine sequence. Something about threading, eval. So it's like in very detail. We have a regular expression engine called Oniguruma, and we have some utility functions also. The interpreter implementation is available with inits main ruby.c, where you initialize your interpreter. This is the multilingualization code, and this is the basic class library. So you can notice that the array.c maps to the array, bignum is maps to the bignum. So these are many classes that are actually built in C, and we use it as a Ruby objects on the top. So definitely we will not go to the details, but let's understand. Okay, so this is the header file ruby.h, which actually describes or defines all the basic structs. So struct is a C type variable. So R basic, we have R object, we have R class which maps to class, float which maps to float, the R string which maps to string class. So let's take a look at R object, R basic, and R class definition. So This is the R object and R basic implementation of the C. So you will notice that the struct R object has two members, basically two members. One struct R basic and other is a union with struct and a value of array including. So we would go about R basic is actually present in all the object structures. We would get to know what R basic is. R basic is actually, it contains two kind of information called flags and class. And if you notice, the type is value. We would come at a later point what value is, but value is nothing but it contains a pointer to an object. Flags are used to actually store which kind of object it is, whether it's a R object, whether it's a R class, whether it's a R string. Okay, it is a, again there are something like frozen object, or we have singleton object. So these kind of information is stored in flags, and class actually stores the class of the object. Now if you notice, we have a struct called st_table, which is a pointer to indexed variable index table. So it actually holds the your instance variables, and this one is the definition of R class, which also holds the method table, that is struct st_table m_table. So struct st_table is another implementation which we would cover when we cover some hash. So it is nothing but basically a key and value pair. So we have the method defined in a class, and we have the instance variables defined in both the R object and R class. Since we don't use the instance variables in other type of objects oftenly, say string or integer, we don't have this struct st_table iv index table in the other objects. Okay, let's take an example. We all know this, the instance specific behavior. Create a object, my object, and we define a method on that instance, that is the my object.hello. So if I call my object.hello, it just returns hello, but if you try to call object.new.hello, then it will return no method error. So how does it actually map to the internal C implementation? Again, the drawing is not to a 1:1 scale. It is a conceptual sketch. So it may not represent the exact objects that are created, but just for our understanding, I have made it simpler. So this is the class that points to the object, and when you define an instance specific behavior on that object, what it does, it creates a singleton class. I have marked it as my object, and it actually the super of the my object points to the actual object class, and where your hello, the singleton method is defined in this singleton class. So how does it map to the actual C implementation? So we can look at one simple method. So this is defined in class.c, and it is actually doing make singleton class and value object. So in Ruby everything is object, and in C everything is a value. So that's why the parameter that is being passed in this is value object, and this is nothing but the R object. And if you notice, what is happening here is we have getting the original class by R basic object the class. So R basic is nothing but a macro which actually casts to a pointer to the R basic struct contained in that R object. So it gets the class, and it would instantiate another class, say value class is equal to RB class boot with original class. So it would set the original class as the parent class of this new class. And if you notice this, then it sets a flag called FL singleton in the new class. So this is where the information is stored in the flags member of the R basic struct, and it would point now the class of the object to the singleton class. So this is how it is implemented in C. Okay, good to know about this. Now let's talk about what a value is. So am I immediate object or am I a pointer? So I told that it is actually pointing to the objects, it's a pointer, but it is not always the case. In C, the typedef is defined, the value is defined as typedef unsigned long. So for a 64-bit machine, the unsigned long is 8 bytes, and it is actually when we say C type for referring to arbitrary Ruby objects. But consider a case when we have some iterator variables where I want to iterate over say millions of integer objects, then it's definitely not wise to create those 50,000 or millions of objects just for iterator variable. Or even when we deal with the true class or false class, it is not viable to create object space for them. So what maths have done, in this value we have the pointers, basically the address of the object, and as well as the immediate object. So what all these immediate objects are: fixed num, symbols, true, false, nil and undef. Undef is a type which is internally used for the interpreter. So these kind of objects, they are actually stored in the value. So it saves memory, it saves execution time, and it doesn't actually hamper the real object model. So but how do I check that whether this value is an actual object or it is pointing to some object in the memory space? So here is a check. So we have a bit set bit test. So if the LSB is 1, then it's a fixed num. If the value is equal to 0, 2, 4 or 6, it's a special constant. So these all are constants defined inside the C: false, true, nil and undef. So it is like Q nil, Q true, Q nil, like that. I think we have checked like when you say nil.id, it always returns 4. So this is how it is mapped. If the lower 8 bits are equal to the I think 14 decimal, it's a symbol. Otherwise, it is an object reference. So this is a pointer. Object reference means it contains the address of the particular object. Okay, great. So let's take an example of R string. Okay, so this is the definition of R string struct in Ruby 1.8.7. So again we have the struct R basic. So it again I would not repeat, but it actually stores the flag and class members, and then we have the long len, the character pointer, and then we have a union of long kappa and value shared. So I think it's clear from the variable names that the len is actually the length of the string. Character pointer actually points to the location where the string is stored. We have a union of long, capacity and value shared. We would come to know about what shared is in the upcoming examples. But if you notice, I think union, the size of the union is the size of the longest or the largest variable, largest member. So in this case, it is again 8 bytes. So the total size of this struct is comprises of I think 23 bytes. 23. Okay. So, and this is the implementation of 1.9.3. It's quite big. Let's take at what is the difference. The main difference is this one. So we have a character array defined with some default length, and that default length is defined at the top. It is size of value into 3 divided by size of char minus 1. So for 64-bit machine, it will come out as 24 minus 1, that is 23. And the difference that I see is the character array addition, and now this entire thing is constructed as a union. So union is of 2 members of struct and this character array. So the effective size of this would be again 23, and that's why this character array is made as 23 character length. Okay, so now let's take some example. So this is a very simple example. I am creating a string. This is a very long string, and just copying the string from str variable to str2. Okay, I am creating one class of debug. It is nothing but a C extension which actually displays the hexadecimal addresses of what are of the structure variables. So let's take a look at one example. So in Ruby, we have string as objects, and in C we have the rstring struct. Okay, so this is how it is stored. So in C we have a concept of heap allocation. So we use malloc and alloc to allocate some memory from the heap area. So most of the times what happens is when you create a string, it creates the rstring struct inside with this character pointer long len, and the character pointer actually locates to the address of the string in the heap area. Okay, and if you notice there is no rstruct, another rstruct created. Both the handles actually share the same rstruct. So we can actually find out the actual memory addresses. So this was the C extension that I was talking about. It is nothing doing but printing the hexadecimal address of the individual struct members. Basically the rstring struct itself, then the pointer and len. And this is how you create a C extension. Okay, I'm not going into detail about, but let's take a look. So this is the output of the earlier program. If you notice, the rstring is the same. So the address of the rstring struct is the same, but the pointer is also same, right? So both share the same location. Okay, now let's take an example of this one. So this is the concept of shared strings. Now here the shared value would come into picture. So in Ruby we have three things. First one is the heap, the shared, and the other one is the embedded. So the optimization technique that I would talk about later. So here we are actually creating an object string.newStr, and the same would occur when you say str.dope. So where you are creating an object. Okay, so how does it, let's visualize this. Now in this case, the two rstructs are created. Okay, rstring, and if you notice, the value shared of the str2, it actually points to the original string objects. And both the structs, they basically share the same data, the same string data. Okay, so this is how, I think for diagram simplicity, I have not shown the reverse way as well. Actually, both the rstruct, both the shared variables contain each other's value. Okay, and we can confirm this with running the debug. Okay, so if you notice now the rstring, the address of the rstring struct is changed now. So they are different, but but the pointer, it again is the same. So the variable pointer. Okay, let's take of another example of CopyOnWrite. Now this CopyOnWrite is a technique which is implemented in both 1.8 and 1.9, and this is very nice because you need not create extra strings unnecessarily. So what will happen if I create a new string object with str.dope and I try to modify the data of that, the string data. So in that case, I cannot use the same string data. So in this case, what happens is, it actually copies the data to another location, and it performs the upcase operation on the next one. And then the character pointer actually points to the individual data in the heap memory. Okay, so this is how the CopyOnWrite technique works. Let's verify this. Okay, so rstring, they are still different. Okay, but if you notice the pointer, they are different. So the addresses, they are different. Okay, so let's talk about now embedded strings. So with 1.9, they have come up with a very good optimization. No, I am actually doing a upcase here, str2.upcase at the last line. Okay. In this case, This one. This one. Yeah. Actually, shared. It actually points to the original R struct. So in this case, it will not point again. So the reference would be removed from that, because now they are pointing to different. So there are two R struct objects, R string objects, and there are two memory locations with two different data sets. So now the value is not shared between these two R strings. Okay. Yes. Yes. Right.
When the second R string object is created.
I think we can take the questions at the end, because I need to cover something, and then we can take the questions. Thank you. Okay. Okay. So I was talking about the embedded strings. So this is the optimization technique that 1.9.3 uses. So this is say a simple example of slice. So I'm creating one string str, and I'm actually copying a part of substring of the original string, the 0 to 3, that is just a this. It is as good as saying str2 is equal to this. So in this case, what happens is, the first str actually points to the heap area. This is a very, very long string, but the other string, which is just comprises of 4 characters or 4 bytes, it actually stores that in an actual character array. So the array that we saw in the 1.9.3, so here there is no need of malloc, there is no need of sharing data, but this value is actually stored directly in the struct itself. Okay, so this is the optimization technique that 1.9.3 utilizes. We can have again look at it. So just modified the debug class that I wrote with the array address as well, and what it contains. So this is how it looks. So the first one, okay, the second one, but if you notice the array value and the array address of the first str, it is some garbage value. By default, C has some auto storage class, so that's why it has come to garbage. And in the second thing, we have array is initialized with this, and we have array. Now this is again interesting that the pointer actually points to the array. So both the addresses are same here. Okay. Now again, this is again one interesting thing, shared strings with slice. Now what happens if I do like this? So if I take a substring which is sufficiently long, so from the first character to the end, or even the second one, so what happens is, now it actually shares the same string data in the heap. So the pointer of the first str points to the first character, but the str2, which has a length of 45 characters, it actually points to the appropriate location of the string. So this is how the shared strings work with slice. Things to be noticed is that the start offset, when you specify for the str, it should lie between 0 to less than the length of the string minus 23. So this is again optimization technique for 23 characters. So if your string is 23 characters or less, then it stores directly into array. But if not, it creates, basically it calls some malloc and it allocates some memory in heap and stores in that. Okay. Let's verify. So if you notice the pointer addresses, so it's been A0 and A1, so it actually points to the A1. So sharing the same string data, and both the array is again some garbage. Okay. So what are the learnings from string? Creating a string 23 characters or less is fastest. Again I am talking about the 64-bit CPU. For 32-bit it is again 11. Creating a substring running to the end of the target, the example that we saw, it is also fast because it shares the same memory. So when sharing same string data, both the memory and execution times are saved because we are using the same data, and there is no special call to malloc. And we know in C the malloc or relloc, the calls are little expensive. And finally, creating any other long substring or string 24 or more bytes is slower. So this is how the string mapping work inside Ruby and C. Let's talk about hash. So this is how the output of hash for 1.8.7 and 1.9.3. As we know that in 1.9.3 we actually maintain the insertion order. So in the second example we actually maintain the insertion order 1, F and 2. Okay, so let's take a look at the implementation. Oh, it's quite complex. So the hash maps to the struct R hash, where we have again a struct R basic. We have a struct st table. St table is nothing but the key value table. We have some called integer iterator leave. I think this is maybe used for I'm not sure, but and the value if none. I think if the key does not map, then it returns nil. So by default the value is nil. And I think this is used for some threading, that interleave, but I'm not aware of. Again, the struct st table that we are looking at, it contains some struct st hash type called type, and we have something called num bins and num entries. Struct st table, we have entry again the bins. So we have a double pointer here. So bins actually points to a location, and that location actually insertion order is maintained. And this is the st table. We have head and tail pointers which points to the first entry of the hash and the last entry of the hash. So things are a little bit complicated, but the traverser is very much fast. If you have some insertions or deletions, then obviously the manipulation is going to take some time, but the traversal of the keys is really very fast. So that's about hash. Before closing my talk, okay. So what we have seen so far is just a tip of the beautiful iceberg. There are certainly many things which are still need to be explored. But I'm sure my talk has encouraged you to take a look at the C source code available, and I'm sure you would enjoy the learnings. So before closing my talk, let's just want to highlight on the C extension part. So why do we use C extensions, and when should we use C extensions? So obvious reason, performance. When we have some already existing C extension libraries, we always use this Nokogiri, Event Machine, MySQL, James, which are the C native extensions. So it becomes helpful when we know the underlying implementation in C. We basically can map what is happening inside the C extensions. And since Ruby interpreter is implemented in C, the API can be used. So I actually did not talk about the different methods. Basically, when you create an array, you create a string. The corresponding method, which is create RB string new or RB array new, is called. So this API, if we know, then the C extensions are very useful. Okay, so thanks to my fellow Rubyist Pat Shaughnessy. He has been a very tremendous support and help for me. The string examples that I have taken are from his blog post, very nicely explained. And these are the image credits. And thank you all for being patient and hearing me out. I'm open for any questions. Thanks a lot.
So based on your research, have you derived any new idioms of doing this or doing that?
Any new?
Any new idioms or new idiomatic ways of writing code based on this research, or
Okay.
it fundamentally change anything for you?
Again, I want to iterate that this study was done for my joy, basically. So I would not say you should not create strings greater than 23 characters. This is not, it is going to work. But how does it actually map to the internal C code? As a programmer, we often, oh, Ruby is excellent, just a one line of code. But what are the efforts that go beneath that one line of code that we should understand? I would not recommend that you should change all your strings less than 23 characters. It is not practical actually. But we should know that what happens inside the C implementation. So okay, so data is shared. That Mads and team, they have actually taken very good efforts, and the algorithms that they have designed, they are optimized. The only thing is that we are not aware of these things. We just, oh, Ruby is great, but the power that lies beneath is unexplored.
Actually, what I'm trying to ask is, did this awareness change anything or any way or the way you write code? I mean, that's what I'm asking. Did this awareness change the way you write code?
Mm, maybe I should say we. So if you come to this example, this is a good example of shared strings, right? So I know that okay, so same data is shared. So I will not create another string with all those data. So maybe again it depends on maybe the programmer how he would take that. Any other questions? Sure.
Uh, so my question is regarding the value.
Okay.
So there are two basic assumptions in using the value in two different ways. One is that uh, the address for that particular architecture is
Okay.
I mean the value is greater than or equal to the
Mhm.
address length required, and secondly that the length of the value is at least 1 byte greater than uh, what is required to store fixed num or
Right.
the other data types. So has Ruby, I mean, is it ported to architectures where this assumption does not hold true? And if that is the case, then how does it work in those architectures? So I mean, there could be architectures where unsigned long is not long enough to store the address of a particular
Mhm.
variable. So what would happen in that case?
So you are talking about what would happen if the code runs on 32-bit and 64-bit like that.
So probably it's true for 32-bit as well, but let's say
Mhm.
I want to port it to uh, some architecture, say at a lower level microcontroller type of architecture or any RISC processor which has smaller by default integer lengths.
Mhm.
So how would it work in that case?
It's a good question. Um, yeah, definitely. I think the unsigned long. If you look at the C source code, they have some if else statements. So based on the system, they are actually type defining the value. So it would be unsigned long, but unsigned long would be different on different machines based on the architecture. So I don't think any optimization for that is present in that. So it would definitely have some downs too. Yeah. Any other question? Or we are hungry? Okay.
So, so I'm assuming that all of this also has been optimized very much from 1.8 to 1.9 in terms of garbage collection. So, have you looked at any of
Mm,
those subroutines?
no,
And
I haven't got a chance to look at the GC or the actual interpreter part. But what I looked at the basic mappings of the objects, the strings, hash, like that.
okay, so next year maybe you can.
Yes, definitely. We're done. Thank you. Thanks a lot.